bifurcations in 2D, and some things that are the same and some things that are different. Chapter 8 of Strogatz. Here's the situation I want you to think about. If we have a 2D system, like we've been looking at, nonlinear in general, if there's a stable equilibrium or a closed orbit, periodic orbit, how can it vanish or change stability as we vary a parameter? That's a question that bifurcation theory addresses. And there's some broad categories. There's bifurcations of fixed points, and they're in two broad categories. Bifurcations related to one of the eigenvalues of the fixed point going to zero. Remember, in general, for fixed points in 2D, we'll have two eigenvalues. But if one of them goes to zero, then it's called a zero eigenvalue bifurcation. And this will give rise to the same sort of bifurcations we looked at before when we talked about 1D systems. So saddle node, transcritical, pitchfork. And what we'll see is that all of the action related to these eigenvalues happens along a one-dimensional subspace. And that's why we focused so much on the 1D systems. The thing that's new, if we have both eigenvalues being on the imaginary axis, this will be called a Hopf bifurcation, and it will give rise to periodic orbits. So this is a mechanism by which a fixed point bifurcates into a periodic orbit, a closed orbit. And like the saddle node bifurcation, it is robust, so it's seen in actual systems. So just to give you an idea, at least about the second one, if we look at the plane of the eigenvalues, so here's the imaginary and real axes of the complex plane where eigenvalues are. So if you're, I'll often use little x's for the eigenvalues. So complex conjugate pair, which if you have something off the real axis, right, the only thing you could have in a 2D system, right, we're linearizing about a fixed point, so that Jacobian matrix A, you could either have a situation where, let's say, both of them are real, and this guy drew lambda 1 and lambda 2 are, say, negative. If you've got even one of them off of the axis, then the other one is its complex conjugate. So they have to come in pairs. And the bifurcation, let's think of this Hopf bifurcation, occurs when we've got things crossing the imaginary axis. So as we vary some parameter, let's say these things start moving towards the imaginary axis, and they'll do it symmetrically, and then they'll cross that axis, and then we'll have a bifurcation. So from the point of view of just looking at the fixed point, we will have something that goes from a stable spiral to an unstable spiral, but due to nonlinear terms, a periodic orbit could show up right at that crossing. So we'll get to that. Let's start looking at the lambda equals 0 bifurcations, because I think those are the easier ones to understand. And then we'll get to the thing that's definitely new in 2D, which is the Hopf bifurcation. The first zero eigenvalue, the kind of one that makes sense to look at, is the saddle node bifurcation. And this will also give some meaning as to why it's called saddle node, when in 1D it didn't quite make sense. The prototypical example, right? So the normal form for a saddle node bifurcation in 2D would be just like we had for the 1D system. We would have something that looks like this. The parameter mu, and then let's say minus x squared. So those are the dynamics in the x direction. In the y direction, we'll say y dot equals negative y. So the x direction, that's where the interesting stuff happens. And we can look at the phase portrait as we vary mu. What are the fixed points? Well, due to the y ODE, y is always equal to 0. Y star, if you want, for the fixed point. What about for x? So we set x dot equal to 0. That gives us mu equals x star squared. So we get x star equals plus or minus square root of mu. So we have two fixed points, x star, y star equals positive mu 0 and negative and square root mu 0. We could draw the different cases to get an idea of what's going on here. If we just recall what was happening in 1D, we'll start with mu greater than 0. Mu greater than 0, that's when these fixed points exist. So they exist for mu greater than 0. So plotting x versus y, we've got fixed point at plus square root of mu and minus square root of mu. The way that the arrows are moving, at least along here, arrows are moving this way and then that way and then this way. Just going back to the 1D analysis. So we might color this one in as an open circle to show that it's unstable and then go from there. The dynamics in the y direction, everything's just collapsing to the x-axis. So everything's going far away. It's all just kind of coming down. And we look at what's happening here. We've got things collapsing to that fixed point, and then nearby they're going to the x-axis and then to the fixed point. What about for the unstable point? It's more of a half stable point because it's got a direction that's stable due to the y dynamics. So that's a saddle. The other one is a node. So what will trajectories do? They'll want to go to the x-axis and then go to the node. In some sense, we could do maybe double lines to show things quickly coming in. So that would be our phase portrait, and we could label these as this is a saddle and this is a node. As we turn the knob of mu, turn it down, right? We're starting at positive mu. Now, as we turn that down, we get to mu equals 0, the bifurcation point. And for that, we'll have these two fixed points merge. We've got this kind of half stable thing. Things are still going to the x-axis, and the flow will still be kind of coming from, on the right side, it'll be coming from the right. And on the other side, it's kind of leaving. So this is a precarious situation. And then for mu less than 0, the 2 points coalesce. So they've coalesced and they go away. So what do we have if we were to plot again x and y? We don't have any more fixed points. There's no fixed points. There will be this region where the fixed point was. So think of mu less than 0, but very small. We'll have a region around here that we'll call a ghost. It's sort of the ghost of merged fixed points. And what do we mean? Well, if we're thinking of magnitude of mu, it's very small, then things will still slow down. For this case of mu equals 0, things slowed to a stop. But in general, a little bit after that, there'll still be something that's almost fixed point-like, a fixed point-like region where things will come in and just move slowly. They'll eventually make it through and they keep on going. And if we had other trajectories, they would all just sort of want to go off to the left. If you remember the discussion about bottlenecks, so this ghost region is also called a bottleneck region because it's as if things are slowing down, as if going through the neck of a bottle. So in this bottleneck region, we can estimate the time that it takes to go through the bottleneck. So the time spent is just proportional to 1 over square root, I'll say magnitude of mu minus mu critical, where mu critical is the value of the parameter at the saddle node bifurcation. So in this case, mu critical is 0. So that means the time spent as things, they go quickly to the x-axis and then they they spend some time in this region. I'm not going to say how big the region is, but they will spend a long time for small magnitude of mu. Okay, it's proportional to 1 over square root magnitude of mu minus mu critical. This is sometimes called a critical slowing down. So if we were going the opposite way, if we had the parameter, let's say very, very negative mu, things are just sort of quickly going through. As we go to negative mu, but small magnitude, we would detect this slowing down, and that's a sign that a saddle node bifurcation is about to occur. So this is actually used to detect saddle node bifurcations in realistic systems. You can detect this critical slowing down. And the focus of this course isn't necessarily on all the tools to show where these types of bifurcations happen in real world systems. I'm mostly just giving you the terminology and background to even identify them. But like an applied nonlinear dynamics course would be one where you actually find this in experimental data. This was a prototypical example, but what about more general systems? What kind of things are happening? This seems pretty contrived. Like, okay, we set it up so everything's going to the x-axis because of how we set up the y dynamics. So what's a more representative situation? And that can be understood in terms of nullclines. If you think of, x dot equals f of x, y dot equals g of x and y. The nullclines are the locations where x dot equals 0 and y dot equals 0. So let's think of just some generic situation. Here's the x dot equals 0 nullcline, which means on here we've got arrows. I don't necessarily know which way the arrows are going, but because x dot equals 0, the vector field is just vertical. It's in the y direction. And we have another curve, the y dot equals 0 nullcline, in which the vector field is only horizontal. If you have the arrows at any point, you know the arrows elsewhere. So let's say the arrows look like that, and then it switches, and then it's like that again. And along the y dot equals 0 nullcline, it would look like this, and then it switches over here, and it switches again over there. So you can kind of get the idea of what other vectors off of the nullclines will look like. There'll be some kind of combination. Any place that nullclines intersect is going to be a fixed point. In this case, what's happening over here? Well, it looks like we've got an arrow going away, an arrow going away. But then over here, arrow kind of coming towards, arrow coming towards. So this is looking like a saddle point. And over here, what's happening? Some combinations of arrows. We've got things going into that point. So this is a stable point and then a saddle point. As some parameter adjusts, the intersection of these two, right? Imagine just changing some parameter. We've got the intersection of these two curves. Instead of intersecting in 2 points, the 2 points will get closer and closer together and then intersect just in 1 point. And the two nullclines would be tangent. And then after that, there's just no fixed point at all. So it's a lot like the way we described the saddle node in 1D, where we said these things show up pretty generically because you could write them. It's just the intersection of something that looks locally like a parabola with something that kind of looks locally straight. And where those curves intersect, you'll have a saddle node. So that's why they're pretty robust. So we can talk about an example in a bit more detail to give you some more of an idea of how this would work. So in this case, we'll follow an example it's a genetic control system. So it's about the activity of a certain gene and how that gene is related to a protein. So this system comes from, think of a genetic regulatory network, and we'll eventually use nullclines to analyze it. But here's the example. in dimensionless form, it'll look like this. So x dot equals negative ax plus y dot equals x squared over 1 plus x squared minus by, where a and b are both positive constants. X is proportional to the concentration of some protein, and y is proportional to the concentration of some messenger RNA that translates that protein. So we don't really need to worry about the details about that for now. Just we're going to analyze this system. And we're going to see, what happens as we vary parameters here. Here we have 2 parameters, so maybe there'll be something interesting related to that. So let's look at the nullclines for this. The nullclines are just given by setting x dot and y dot equals 0. So the x dot equals 0 nullcline is particularly simple. It's y equals ax. And then what about y dot equals 0? That is given by y equals x squared over b1 plus x squared. We want to suppose that we will be varying a while we hold b fixed. So holding b fixed means that this curve over here is fixed. We've seen this before. We encountered this curve. It's got a kind of an S shape, so it's called a sigmoid curve. We encountered it in the insect outbreak. Remember that this was related to the effect of predators. So if I were to plot what the nullclines do, I guess since we're looking at concentrations of things, we're also just looking in the first quadrant. So x and y both positive. The sigmoid curve, the general shape will be, it's kind of the way that we interpreted before. It'll kind of rise and it reaches its kind of greatest rising at, in this case, around 1. And it's going to be asymptoting to 1 over b, right? Think of x going very, very large. Then x squared over 1 plus x squared is about equal to 1. So this goes to about 1 over b. So this is that sigmoid curve. And we're going to think of the b is fixed and y can vary. As y varies, what is this? This is just a straight line. So this is a straight line that makes it easier to kind of move around. If we think of a being smallish, it'll be small enough that it'll intersect this curve multiple times. So there's y equals ax. Whenever there's an intersection of these nullclines, we have fixed points, and we want to know a little bit more about these fixed points. In fact, where will these, as we adjust that a curve, so imagine we kind of adjusted it, and then at some point it'll just be exactly tangent. That's tangent. And then beyond that, it won't be. So what's the value of a when the straight line is tangent to the sigmoid curve at the top part of it? This is getting kind of cluttered, so I'm going to just sort of get rid of that. So this will happen. I'll just do the one. It's tangent. So this would be y equals, we'll call it acx. So there's some critical value of a where we have this tangency. How do we solve for that? Well, at that point, the 2 curves will equal each other. So we can find out. Let me just look at everywhere that the 2 curves intersect. Everywhere they intersect, we get fixed points. So just setting them equal to each other, right? They're both written as y as a function of x. So just set them equal to each other. Ax equals x squared over b1 plus x squared. So one solution is x star equals 0, which, yeah, we know. There's a point over here of intersection. Maybe I'll plot it in some color. So there's an equilibrium point at both x and y being 0, but what else? The other one, we can divide by x and write AB1 plus x squared equals x, which we can solve using the quadratic formula. So this has two solutions. X star equals, the denominator is 2ab, and then up above is 1 plus or minus square root 1 minus 4a squared b squared. So we've got that. This has two solutions when the thing under the square root is positive. So 1 minus 4a squared b squared greater than 0, which is another way of saying 2ab less than 1. And there's only one solution when that equals 0. When 2ab equals 1, so that would be, that gives us the critical value of a. So it's 1 over 2b. And if you put that in here, so when there's one solution, the thing inside the square root goes away, and that 1 point ends up being at 1 over 2ab. But hold on, 2ab equals 1. So this happens at 1. So interestingly, 1 is where that sigmoid curve goes up, and that's also where we have the critical point. So if I were to draw this again, it's right above there. So this is at AC equals 1 over 2b. The two solutions are for A less than AC, right? Smaller A, shallower slope, will have the two points of intersection. We don't know yet, which one's positive, which one's negative. I mean, which one's stable, which one's unstable. But we've got those 2 points, and one of them is going to have to be at x star less than 1, and the other one's at x star greater than 1. So if we were to do this, this is x star less than 1, x star greater than 1. So we can plot, I'm going to replot these nullcline curves and then put in some arrows so we can get an idea of what's going on. X, Y, we've got our sigmoid and the other curve. And remember what this one was. This was x dot equals 0, and this curve is y dot equals 0. So now we could put in arrows. If you just need to evaluate at one point, and you'll find out what the arrows, which way the arrows are going. So it turns out the arrows are down here, which means when you cross a nullcline, it switches signs. So then it would switch back over here. We got this, and it's hard to draw it anywhere else. So we have this and we have that. So this looks like the situation that I sketched up above. So things are moving away. Things are moving away in one direction and then coming closer, in the other direction. And then over here, things are just sort of coming in from all directions. So we've got a saddle and a fixed point. We're not yet sure if it's a node or spiral. It's in the category of sink because things are going in. If you remember what a sink was, so sink, which means a stable node or stable spiral. And the details would depend on sort of where we were on that curve of the trace versus the determinant of the Jacobian matrix. But this one definitely looks like a saddle. If you have things coming in and things going out, that's all you can be, is a saddle. And if this follows the formula, that pattern in 1D that the fixed points have to alternate stability type, that would mean that the thing over here this is just stable. We don't really care what type necessarily, because that one doesn't participate in the bifurcation. So if we want to know about what exactly this sink point is it a stable node or a stable spiral, we would calculate the Jacobian. So the Jacobian of this vector field up here, that's the vector field. Keep that in mind. We'll write the Jacobian. So Jacobian at a general x and y is going to be what? Negative a1. That's for x dot, that's easy. And then this will be 2x over 1 plus x squared minus b. And we can then plug in what we know for those fixed points and maybe simplify and get some insight about it. There's something we can notice already before even knowing what the particular x and y are, and that's the trace, right? Trace of a. In this case, it's minus a minus b. We're combining them. And we know that a and b are both positive, so that means this is less than 0. It means that in that diagram of tau versus delta, we're in the negative half plane. That looks like an A. It should be a delta. So we can calculate delta. At 0, 0, what's the determinant? The determinant is just going to be A times B, which is greater than 0. So that's going to be, if we were to plot this parabola that separates, if you remember what this was, this is tau squared minus 4 delta equals 0. Everything inside here is, inside the parabola is tau squared minus 4 delta less than 0. And everything outside on kind of both sides here is tau squared minus 4 delta greater than 0. So if we've got that going on, we can find out that, what is it? Tau squared minus 4 delta. If you work that out, it's A minus B squared. So that's going to be, in general, greater than 0. So that means we're over in this yellow region, so where tau squared minus 4 delta is greater than 0, and those are the nodes. So if we're negative tau and we're in the node region, right, we're somewhere over here. So these are stable nodes. And then if I were to, maybe this is a little bit too vibrant. These are what? Spirals. Down here would be stable spirals. So this fixed point is a stable node. Okay, that's good to know. Maybe we can even fill it in up here. It's a stable node at the origin. What about the other two cases? Well, for the other two cases, remember we're thinking A less than that critical value. You could work out that delta is AB times x star squared minus 1 over x star squared plus 1. The middle point, which is middle point, has x star less than 1. So that means delta is going to be negative, which means we're over here somewhere in the realm of the saddles. So that's a saddle. That makes sense. And for the other one, delta will be positive. So the right point has x star greater than 1. So delta is positive. And again, if you work out what it is for that point, for that right point, you'll have tau squared minus 4 delta being greater than a minus b. And so that means it's greater than 0, which means, again, we're in the stable node region. So now we know exactly what type of sink it is. If you want me to put that classification again, it would be for things delta greater than 0, these are sources, and less than that would be sinks. So that includes stable, but not, we don't necessarily know which type. If I say sink, it could be a node, or it could be, spiraling. Another thing to notice would be at that bifurcation point itself, what do we get for the eigenvalue? At the bifurcation point, right, A equals AC, that gives us X star equals 1. So if X star equals 1, that means delta equals 0. And if delta equals 0, you probably don't remember what the formula was for the eigenvalues as a function of tau and delta, but it was the two eigenvalues. The formula is 1/2 tau plus or minus tau squared minus 4 delta. So if delta equals 0, then we have tau and 0. So we've got an eigenvalue 0 is the key thing. Notice one of the eigenvalues is 0. Now, what do things look like in terms of the dynamics? This is what they'll look like if we do it a phase portrait. And before the bifurcation, so A less than AC. We've got X and Y. The origin is a fixed point. Somewhere over here, the middle point is a saddle. So that means there's going to be some direction coming in, some direction going out. And then over here will be another stable fixed point, a saddle node. So that means there'll be some direction coming in very strongly and some direction coming in less strongly. It turns out, right, these will be connected. So there's some direction here where things are coming in less strongly, and then the other direction they're coming in very strongly. Actually, it's the opposite. I've got the really strong direction coming from here. So things will be quickly collapsing to what seems like one curve, quickly collapsing. And maybe I'll highlight this stable manifold. That's the name of it. It has two branches. It's the stable manifold. Think of just continuing the stable eigendirection until it stops being straight, starts curving. It's got two branches. So let's say the positive branch and then this lower branch down here too. So trajectories will be nearby that will be coming in quickly to this, what seems like this one-dimensional curve, and then going toward that node. What about on the other side of this? Well, they'll be coming in and then they'll go towards there. So it's looking like the stable manifold of the saddle acts like a threshold. The technical term is separatrix because it separates two qualitatively different types of behavior. And the biological interpretation would be that it determines whether the gene turns on or turns off, depending on the initial concentration of X and Y. Remember, this was related to the concentration of some messenger RNA and a protein. So if you're above that stable manifold, then you will be going to the on switch. You'll be settling down to something that's stable. And if you're below, then you'll be going down to the 0, 0, basically turning off. So in some sense, this is a model for a genetic switch. And as you vary the parameter A, right, when those two coalesce, then the only fixed point that remains is the 0, 0, meaning this gene is only turned off. So that's our biological interpretation. We have sort of a genetic switch turning on or off, and it just depends on where you were, like the basin of attraction of one fixed point or the basin of attraction of the other one. And if this A thing, the parameter A, is varied by some other part of the biological system, you could only have off if desired by the system. You can get similar stuff happening with the Pitchfork and the transcritical. Before going on to that, one of the main things to notice is that fundamentally things are just happening in 1D over here. All the action is happening on a 1D curve where the fixed points slide like beads as you vary the parameter, which suggests that bifurcations are essentially one-dimensional. They happen in some one-dimensional subspace. Single zero eigenvalue bifurcations are fundamentally 1D phenomena. And here it's 1D in a 2D space, but they're fundamentally 1D phenomena even if we were in an n-dimensional space, which is pretty amazing. I've got another video, actually a video series that goes over this, but this is justified by something called center manifold theory. The general idea there is when you have an eigenvalue 0, so at these bifurcation points, there is an eigendirection associated with that eigenvalue 0. So if we have our sort of coalesced fixed point, we've got some local eigendirection, and we sometimes call this EC for the Euclidean space spanned by it. And it is along some curve, which we write as WC. This is manifold notation. So there's this curve, and you could look at the dynamics along the center manifold, which is just 1D, and all bifurcations occur along center manifolds. When you have a single zero eigenvalue, there'll be a one-dimensional center manifold. And what really matters is actually the real part of the eigenvalue. So for the case where you have a single zero eigenvalue, then this would be the corresponding eigenspace and manifold, and forget about all of the other eigenvalues. All that matters is, okay, if you've got an eigenvalue that is at 0, then there'll be this sort of new subspace that shows up, the center manifold, and bifurcations are likely to occur. And you won't see it in the linear part. You have to look in the nonlinear part to get at those bifurcations. So we look at the dynamics reduced to the center manifold. You can have the case where there are two eigenvalues. You could actually have a double eigenvalue 0, but we won't talk about that case. If you have two eigenvalues that are on the imaginary axis, so that means two eigenvalues with the real part of lambda equals 0, then you have a two-dimensional center manifold. And this could be embedded in an n-dimensional space, but it means all of the bifurcations will happen on that two-dimensional subsurface. And this is actually where the Hopf bifurcation is related to that. This is an aside. You don't be scared. If you want to know more, you can look into it. But there is a rigorous justification for why these zero eigenvalue, these bifurcation phenomena seem to all be kind of happening in 1D. And it's because they are. It just is. So for the transcritical, you could do similar studies. So similar for the transcritical bifurcation and the Pitchfork. These things could be embedded in a higher dimensional space. In fact, we saw an example of the Pitchfork bifurcation in an earlier system where let's do the Pitchfork just quickly. If we look at the prototype or a normal form for it, x dot equals, I'll write this as ax minus x cubed. And then in the y direction, make it nice and boring. Y dot equals negative y. Then for a less than 0, what do we get? We could look at the Jacobian, a 0, 0, negative 1. In terms of what our eigenvalues are doing, there's one at negative 1, and there's one at a, right, which is negative. This is at the origin. Got a fixed point only at the origin. It looks kind of like a stable node. And then there'd be the critical case of a equals 0. as we tune A from negative to positive, there'll be the critical case, A equals 0, and at little a equals 0, look at what we get for the eigenvalues. Right, you could just read them off the diagonal. It's 0 and -1. Ooh, interesting. Eigenvalue 0. Okay. So that, well, I've been doing little x's and -1. And it's going to look very similar. Things will be kind of coming in, right? In x dot, this just looks like -x cubed. So unlike the saddle node where things were coming in one side and then kind of going out the other, here from both sides, it's coming in. And then for a greater than 0, now you pick up 2 new fixed points. Now, instead of just the origin, we've got other points. So yeah, what do we have at the origin? The origin becomes, now we've got A on the right half side. So we've got a saddle at the origin. We write y and x again. This becomes a saddle. Things are still coming in along the y direction towards x. So that is the stable direction. But then things are moving away along the x-axis, and they're going to these points, these fixed points, which if you work out what they are, they'll be symmetrically located, and we have 2 new fixed points along the x-axis. So at x star equals plus or minus square root of a, which is now positive, and y star equals 0. They'll be stable nodes. So this looks a lot like a phase portrait we did either 1 or 2 lectures ago. They're stable. So it looks like the Pitchfork, but in 2D. That's it for today. We'll talk about the hop bifurcation next time. So that's the one where it gives rise to a fixed point, can give rise to a periodic orbit. And there's 2 different types, just like there's 2 different types of Pitchfork. You know how we've talked about subcritical and supercritical. This is actually an example of a supercritical Pitchfork bifurcation. Why is that? It means that the new fixed points are stable. If we reverse the sign, I think if we turned this into a plus, then the bifurcation would be going the opposite way, and we would have the 2 new fixed points be called subcritical, and the fixed points would be unstable. So that's that. So yeah, next time we'll do hop and all the cool stuff related to it.